Hey there, science fans. Today we're diving into the world of MOSFETs. MOSFET stands for Metal Oxide Semiconductor Field Effect Transistor. That's a mouthful, right? Think of MOSFETs as tiny electrical switches that control the flow of electricity. They're like the ones and zeros in a computer, turning things on and off billions of times a second. MOSFETs are everywhere in our electronic devices. They're in our smartphones, computers, TVs, and even cars. Without these tiny switches, our modern world wouldn't be possible. MOSFETs are the unsung heroes of the digital age, working tirelessly behind the scenes. They make our lives easier and more connected. These little marvels of engineering are incredibly small, with billions of them fitting on a single computer chip. Their small size allows for powerful and compact devices. They're also very energy efficient, using very little power to operate. This efficiency is crucial for mobile devices that rely on batteries. Just like ice cream, MOSFETs come in different flavors, well, types. The two main types are depletion mode and enhancement mode MOSFETs. Don't let the names intimidate you. They're easier to understand than they sound. Depletion mode MOSFETs are like a faucet that's already turned on. Current can flow through them even when the gate is off. We'll talk more about the gate later, but for now think of it as the switch. To stop the flow, you have to apply a negative voltage to the gate. Enhancement mode MOSFETs are the opposite. They're like a faucet that's turned off. No current flows until you apply a positive voltage to the gate. These are the most common type of MOSFET found in most modern electronics. The type of MOSFET used depends on the specific application, depletion mode. MOSFETs are useful for amplifying signals, while enhancement mode MOSFETs are better for switching applications. Let's peek inside a MOSFET and see what makes it tick. Imagine a tiny sandwich with four important parts: the gate, the drain, the source, and the body. The gate is like the control knob on a faucet. It's a metal layer separated from the body by a thin insulating layer, usually made of silicon dioxide. The drain and source are like the two pipes connected to the faucet, allowing water, or in this case current, to flow. They are semiconductor regions doped with impurities to make them good conductors. The body is the base of the transistor, usually made of silicon. When you apply a voltage to the gate, it creates an electric field that penetrates the insulating layer and influences the flow of current between the drain and source. This electric field acts like an invisible hand, controlling the flow of charge carriers, which are like tiny boats carrying electrical current. Now let's see how this tiny sandwich actually works as a switch. Remember, MOSFETs control the flow of current using an electric field. When a voltage is applied to the gate, it creates an electric field that affects the channel between the drain and the source. In an enhancement mode MOSFET, a positive voltage applied to the gate attracts electrons to the channel region. These electrons form a conductive path between the drain and source, allowing current to flow. The higher the gate voltage, the stronger the electric field and the more current can flow. In a depletion mode MOSFET, the channel is already formed, and a negative voltage applied to the gate repels electrons from the channel, reducing its conductivity and thus the current flow. The more negative the gate voltage, the less current can flow. Section 5. Depletion versus enhancement, turning the switch on. The main difference between depletion mode and enhancement mode MOSFETs lies in how they are turned on. Depletion mode MOSFETs are normally on, meaning current can flow through them without any gate voltage applied. Think of it like a water valve that's already open. To stop the flow, you need to apply a negative voltage to the gate, effectively pinching off the channel and stopping the current. Enhancement mode MOSFETs, on the other hand, are normally off. No current flows between the drain and source until a positive voltage is applied to the gate. This positive voltage creates the channel, allowing current to flow. It's like a closed water valve that needs pressure to open. The higher the gate voltage, the wider the channel opens, and the more current can flow. Section 6. MOSFET Parameters, the need-to-know specs. Just like any electronic component, MOSFETs have specific characteristics that determine their performance. These are called parameters, and understanding them is crucial for designing and using MOSFETs effectively. One key parameter is the threshold voltage, or V. This is the minimum gate voltage required to create a conductive channel between the drain and source in an enhancement mode MOSFET. It's like the pressure needed to open that water valve. Another important parameter is transconductance, or GM. This measures how effectively the gate voltage controls the drain current. A higher transconductance means the MOSFET can switch current more quickly and efficiently. Finally, drain source resistance, or RDS on, is the resistance between the drain and source when the MOSFET is switched on. A lower resistance means less power is lost as heat, making the MOSFET more energy efficient. Section 7, MOSFETs at work, from smartphones to spaceships. MOSFETs are incredibly versatile devices used in a wide range of applications. They are the building blocks of modern electronics, found in almost every electronic device imaginable. In computers and smartphones, billions of MOSFETs form the logic gates that process information. They act as tiny switches, turning on and off at incredibly high speeds, allowing for complex calculations and data processing. MOSFETs are also essential for power electronics. They're used in power supplies, inverters, and motor controllers, efficiently converting and regulating electrical power. From powering our homes to driving electric vehicles, MOSFETs play a crucial role in our electrified world. These tiny transistors are also essential for amplifying signals. They are used in amplifiers, radios, and other communication devices, boosting weak signals to make them audible or transmittable. Section 8. MOSFETs versus BJTs, a tale of two transistors. MOSFETs are not the only type of transistor out there. Another common type is the bipolar junction transistor, or BJT. While both MOSFETs and BJTs amplify and switch electronic signals, they work in fundamentally different ways. BJTs are current-controlled devices, meaning the current flowing through the base terminal controls the current flowing between the collector and emitter terminals. MOSFETs, on the other hand, are voltage-controlled devices where the voltage applied to the gate terminal controls the current flow between the drain and source. This difference in control mechanism gives MOSFETs several advantages over BJTs. They have a much higher input impedance, meaning they draw very little current from the control circuit. This makes them ideal for use in battery-powered devices where low power consumption is crucial. MOSFETs are also faster than BJTs, making them suitable for high-frequency applications. They're also more resistant to electrostatic discharge, making them more reliable in harsh environments. Section 9. Weighing the pros and cons of MOSFETs. Like any technology, MOSFETs have their own set of advantages and disadvantages. Understanding these trade-offs is essential for choosing the right transistor for a specific application. On the plus side, MOSFETs offer high input impedance, meaning they draw very little current from the control circuit. This makes them extremely energy efficient, a crucial factor in battery-powered devices. They're also faster than their BJT counterparts, making them suitable for high-frequency applications. However, MOSFETs are more susceptible to damage from electrostatic discharge due to their thin insulating layer. This requires careful handling and protective measures during manufacturing and use. They are also more sensitive to temperature variations, which can affect their performance. Section 10. MOSFETs, powering our electronic world. From the smartphones in our pockets to the computers on our desks, MOSFETs are the unsung heroes of the digital age. These tiny switches have revolutionized electronics, enabling the creation of smaller, faster, and more powerful devices. Their ability to control current flow with minimal power consumption has made them indispensable for a wide range of applications, from communications and computing to power electronics and beyond. As technology continues to advance, we can expect MOSFETs to play an even greater role in shaping our future. Understanding how MOSFETs work allows us to appreciate the ingenuity behind our electronic gadgets. These tiny transistors are a testament to human ingenuity, constantly evolving and improving to meet the demands of our increasingly digital world. Please follow me for more content on the fascinating world of electronics.